Okay, good morning, everyone. That seems just a little on the loud side. Can you still hear me okay in the back? Okay. Does anybody have any questions before we begin this morning? Over anything, Unit 2, Unit 3, what we started on Unit 4 last time? All right. Then if not, what I would like to do is continue our discussion of data security. So you remember last time we started off talking about this data security unit, and in particular we sort of jumped into this idea of public key cryptography, and I said we would define that term later. We should get to that today. But we gave us sort of this original example, this idea of Diffie-Hellman exchange. The big idea that we're trying to get at here is how do we get two parties to agree on a cipher? So we're going to use some sort of cipher, some algorithm to encrypt and then subsequently decrypt our messages. But we need both people to agree what's the cipher that we're going to use. Because if I encrypt it with 1 and I send you the message and you don't know the correct decryption protocol, is it going to matter that we encrypted the message? No, because you're not going to be able to decrypt it, and that makes it very, very secure to the point that it's not useful. And so the key challenge that we have is how do we get these two parties to agree on the algorithm, especially when it's not likely that they're going to meet in person. We discussed maybe last time the two parties could have a meeting before they wanted to start doing privileged communication and say, oh, here's the cipher we're going to use. And if that works, that's great. But in the general sense, when we're talking about doing data security with email or with online banking, does your computer ever directly hook into your bank's computer before you start doing online banking? No, you're going to access it through the internet. Okay? And so the one sort of key example that we had last time was this idea of Diffie-Hellman exchange, and we went through this nice paint example where we could think about there's this common color at the beginning, and everyone has their secret color, and we can make public colors from our secret colors, and we can exchange those, with the idea being, if someone were to eavesdrop or try to intercept these public parts that are communicated, so Alice shared this orange color with Bob, Bob shared sky blue with Alice, if Eve were to intercept those communications, it is very hard for her to determine those secret colors, either the slightly darker orange for Alice or the teal for Bob. Very, very hard for Eve to determine those colors given what is publicly sent. And it turns out this is a really nice analogy for how Diffie-Hellman and how other systems, public key cryptography systems, actually work. And we wanted to use this as sort of our motivating example. So we then jumped in and said, well, we've got to see some math concepts before we can get into how does Diffie-Hellman actually work? What are the equations? How do they go about doing this? And we got about, 2/3 of the way through that discussion. And so just to review last time, we spent a little bit of time looking at modular arithmetic, where now we said, how do we maybe add numbers or subtract numbers or multiply numbers, and then take them modulo n. So from last time, what was sort of the big example in day-to-day life of where we use modular arithmetic? It was clock math. So we know we can take whatever our minutes are and we add some minutes to it, and the minutes ultimately have to be between 0 and 59. Likewise, we can carry extra minutes into the hours digit, but the hours have to be between 1 and 12, and so on and so forth. This is modular arithmetic. And then at the very end of lecture, we started talking about some number theory. And we introduced the greatest common divisor, or GCD, and worked through a couple examples. And we saw there was this idea called Euclid's algorithm. This GCD AB equals GCD B and A mod B as a way to compute greatest common divisors relatively quickly and easily. And then basically where we sort of ended last time was this idea of looking at prime numbers, things like 2, 3, 5, 7, 11, 13, and so on. Integers that cannot be written as products of other integers, which is to say they're only divisible by 1 in themselves, okay, over the integers. And where we ended last time was this idea of looking at prime factorizations. We would say take some integer, and we can write it in a unique way as a product of prime numbers. And so for our two examples, we saw that 12, just here on the lecture notes, there are 2 factors of 2 and 1 factor of 3. And so if we write 2 times 2 times 3, that's a unique way to write 12 as a product of prime numbers. And we sort of ended lecture with this big example of looking at the number 29,400 And after going through this a little bit, we found that it had 3 factors of 2, 1 factor of 3, 2 factors of 5, and 2 factors of 7. Okay? Does this ring a bell to everyone from last time? Okay. So where are we going with this? Well, prime factorizations are nice for a couple reasons. They're going to be important in some of the work that we're doing later. Basically, the cryptography algorithms don't necessarily need the prime factorization. Why I'm including this, if Eve were to intercept the data that we're going to share later, if she were able to do a prime factorization quickly, she would be able to break the encryption system. Okay, so we're not necessarily going to need to do prime factorizations, but I want you to understand what goes into cracking these codes. That's what the eavesdropper is doing. That's when the NSA has their big supercomputer and they're filtering all your emails and trying to read what you're writing. They're basically sitting there trying and using trial and error. What are different ways to factorize these big numbers? And what are the prime numbers underneath them? Okay? One other thing that's sort of neat with prime factorizations, just as sort of an aside, is it's very straightforward to determine what is the greatest common divisor of 2 integers if you know the prime factorization of both integers. Okay? So for instance, we've got an example here, and suppose we've got a number a equals 60, and we've got a number b equals 126. Is it immediately obvious to you what the greatest common divisor is just from looking at those 2 integers? Not necessarily. Okay, well, if that being the case, we could certainly use Euclid's algorithm that we saw last time, and we could go through that whole recursive thing where we swap the order and take moduli, and that'll work just fine. We can also look at the prime factorizations. And so we can go through and see, is 60 divisible by 2? Yes, that gives us 30. Is 30 divisible by 2? Yes, that gives us 15, which is 3 times 5. And so we can get that the prime factorization of 60 has 2 factors of 2, 1 factor of 3, and 1 factor of 5. In a similar way, our number 126, we could get the prime factorization to show that it's 2 times 3 times 3 times 7. And if we want to look for the greatest common divisor, all we have to do is sort of compare what are the common elements in these 2 prime factorizations. So for instance, do both numbers have 1 factor of 2? Yes. Okay, so does that tell us, is 2 a divisor of both numbers? Yeah. Do both numbers have 2 elements of 2 in their prime factorization? No, only one of them does. So is 4 a divisor of both a and b? No, it only divides a. Okay, so likewise, is there a common factor of 3? Yep. Are there 2 common factors of 3? Nope. Is 5 a common factor? Nope. Is 7? Nope. Okay, and so what we notice is that both of those numbers share 1 factor of 2, 1 factor of 3. If we identify those out and multiply them together, we're going to get 6. And it's pretty straightforward to see then from this prime factorization, does 6 divide 60? Yeah. Does 6 divide 126? Okay, maybe that was a little bit harder to see, but yes, you'll get 21 times. Okay? But you can end up using those prime factorizations, identify what are those common factors between both numbers, and that's going to give you the greatest common divisor. And so if you were so inclined, you could go through and use Euclid's algorithm again, and you would find that the greatest common divisor of those 2 numbers is exactly 6. Okay? So again, this is just sort of 2 alternate ways to do the same thing. Computationally speaking, Euclid's algorithm is much nicer for doing this than doing the prime factorizations, but if you wanted to do it and the numbers were small enough, this will work just as well, too. Okay? And so sort of the last element of number theory that we're going to need before we go on is one other idea of what's called relatively prime numbers. So we've seen a prime number, which says an integer is prime if it's only divisible by 1 and itself. What we'll now do is say 2 integers, a and b, are relatively prime if they share no common factors in their prime factorization. Okay? So from our last example on the last slide, would 60 and 126 be relatively prime? No, because they shared a factor of 2 and they shared a factor of 3. Okay? And so another way of saying this is that 2 numbers are relatively prime if their greatest common divisor is 1. Okay? So we can do some examples. Are 4 and 27 relatively prime? Yep. This is probably a little bit straightforward to see. What's the prime factorization of 4? It's 2 times 2. And what's the prime factorization of 27? Right, it's 3 times 3 times 3. So we can get 4 is equal to 2 squared. 27 is equal to 3 cubed. Are there any common factors between those two? No, so the greatest common divisor has to be 1, and they're relatively prime. If we were to look at 12 and 63, can we find a common factor between 12 and 63? Yep, and what would that be? 3. Because 12 divided by 3 is 4, and 63 divided by 3 is 21. Is the greatest common divisor of 12 and 63 then 1? Nope. It's at least 3. I think it actually turns out to be 3 in this case. But we don't need to know specifically what it is. We just know it's not 1. So are 12 and 63 relatively prime? No, they're not. Okay? And again, if you want to see some more information on relatively prime numbers, there's a link there to Math World. Okay, so sort of the last slide that we'll have in sort of this math concepts part here is sort of talking about why were we interested in these math concepts, in this modular arithmetic and all of this number theory. We brought in greatest common divisors and prime numbers and these relatively prime numbers. And they basically have two purposes. And let's maybe do them out of order from what's written on the slide here. As we'll see momentarily, all of these tools, whether it's the modular arithmetic, prime numbers, all of this, are going to help us set up our cryptosystem. When we look at how Diffie-Hellman and how the RSA algorithm works a little bit later, we're going to see these concepts play a very central role. Okay? And so we needed to have a little bit of practice with them to be able to work through what's going on. Okay, so then coming back up to the first point, is that all of this number theory, and this is something we're absolutely not going to do in this class, but I just want to make you aware of, is that this number theory can prove that our ciphers, whether we're using the algorithm for encrypting or for decrypting, it can prove that they work. Okay? Which is to say, if I encrypt the data using these tools, as we'll describe in a little bit here, I send it to you and you decrypt it with the proper tools, will you get the message I sent you? Yes. Okay? If that wasn't the case, if we couldn't prove that, would we want to use that for our cipher system? If I sent you an encrypted message and you decrypted it using quote-unquote the proper algorithm and you had an 80% chance of recovering my message, is that useful? Not even close. Okay? And so what's going on here is, from a more general perspective, what this number theory and all of this modular arithmetic is helping us do is show that the encryption routine that I'm going to use on my end before I send you the message and your decryption routine on the other end are inverses of each other. Okay, with the idea that I can do something to the data on my end, I can encrypt it, I send it to you, and when you use that decryption routine, you get back exactly what I originally put in. We can undo that operation. And again, if that wasn't the case, if we didn't have that inverse property, would we want to use it as a cipher? No, that's going to be a terrible way to encrypt and decrypt, because then you're not guaranteed to decrypt and get what I originally put in. Okay, does that make sense? All right, so now we're at the point where we can start to think about how do we convert all of these paint colors to numbers. So as we mentioned just a few minutes ago and discussed quite a bit last time, we had these color examples where, you know, Bob and Alice had this common paint at the beginning, and they each picked a secret color, and they derived this public color from their secret color and the common color, and they exchanged things. And at the very end, the key thing was they both had this common secret. Okay? And so remember, that's where we're going to. But more specifically, they had this common secret, but they never actually shared their own secret colors. So there was sort of this secret information, this private information that Bob never shared with Alice, and Alice never shared with Bob. Okay? And again, that's sort of the key. They're only sharing information derived from that secret information, such that if the eavesdropper or Eve were to intercept the information that actually is shared, it's very, very hard to get back what were these secrets that Bob and Alice have privately. Okay, so how does this work? All right, so remember, the idea was when we're setting up Diffie-Hellman or we're looking for the cipher, we needed this idea of a key, because that was what was going to specify our entire cipher. It turns out the algorithms that are used in cryptography are very widely known. in terms of step 1, do this, step 2, do this, step 3, do this, but they depend on these key values. And these keys are going to be numbers. And depending on what number you use for the key will affect how the actual cipher works, and then how my text is encrypted, and then how once you receive it, it gets decrypted. And so the way it's going to work, at least within Diffie-Hellman as our first example, the key that we're going to have, which will denote k, is just going to be equal to some value g to the power a times b modulo n. Okay, so we can immediately see we've got our modular arithmetic in here, so we've got a mod n, and we've got our exponentiation in there, because we've got this g to the ab. And in practice, g, a, and b are going to be very large numbers, maybe on the integers on the order of 100 digits long. Okay, that's a big number. So is g to the a times b going to be an astronomically big number? Oh yeah. And n is probably a little bit larger, more on the order of 300 digits. Okay, so this is sounding like something really complicated and really tedious, right? Okay, we have computers that can do this. We're going to work through examples with much smaller numbers. Okay? And so the way it works, Bob and Alice originally share some information, and they're going to agree on g and n at the beginning of this setup. So that's sort of their common color. That would be that yellow color that we had up here. What's the value of g? What's the value of n? And then a and b, the other two variables that we need here, are going to be the secret colors. And we'll say A is Alice's secret color, B is Bob's secret color. This is that private information that they generate that they're never going to share with anyone. Okay? And so then what Alice does is she's going to compute this value, we'll call it k sub a, which is just now g to the a mod n. Okay? Is there anything maybe complicated in doing that? Not really. Might be tedious, but not particularly hard. And this is going to be her public color. This is that color she's going to share with Bob. Likewise, Bob is basically going to do the same thing. He's going to calculate this other thing we'll call KB, which is now g to the b mod n. Okay, so remember, both Bob and Alice know g and n. They agreed on that at the start. Bob has b. Again, he can compute this just like Alice computes a. And this is his public color, what he's actually going to share. So what do you think happens next? Now that Bob and Alice have these g and n and ka or kb, what are they going to do? Let's come back up a slide and see. So we've got yellow here is our g and n. Maybe this orange here is a. The teal here is b. This lighter orange or this peach color is our ka. Sky blue is kb. What's the next thing that's going to happen? We're going to swap. Question?
Wait, is that after, is that like their own separate colors? Is that the yellow, or is that like
So those two values that they agreed upon in the beginning, that g and n, are the yellow. And then basically a is this darker orange color, because that's only known to Alice. B would be teal, and then our ka and kb are the peach and the sky blue, again, because they're derived using the secret color, but they're not the secret themselves. Okay, and so the next step, once we have all of this, Alice is going to send her ka value over to Bob. Bob is going to send his kb value over to Alice. Okay? And then what they're going to do is a little bit more to say, well, now let's actually use our own personal secret color again to ultimately get what's that common secret, what's that key, that value k, that says, here's the cipher we're using. Okay? And so the way that works, it looks a little bit weird. Remember, what they're both ultimately interested in is the key k, which from up above we just have as g to the ab mod n. But we can use properties of multiplication to just write that as the number g to the a to the b mod n. And if we go back and use some of our properties from modular arithmetic, we can actually just write this as ka to the b mod n. Okay, so if Bob wants to know that common secret, that value k, that turd brown color on the last slide, he needs to know three things. He needs to know ka. Is Alice willing to share ka with him? Yeah, because that's her private or her public part. Okay? Does Bob know b? Yep, that's his own private secret. And does he know n? Yeah. Alice and Bob agreed on n at the start. And so does Bob have everything he needs to be able to get the actual key k? Yeah. Okay. Alice, it turns out, the exact same thing happens. She wants to calculate this same value, only now instead of writing this as g to the a to the b, we can do g to the b to the a. Doesn't matter which order we're going to do that. And so Alice can compute the private key, or that private secret, as k to the b, or kb to the a mod n. And does Alice have kb? Yeah, that's the information she got from Bob. Does she have a? Yep, that's her own private secret. And does she have n? Yep, Bob and Alice agreed on that at the start. And so in that way, did Bob and Alice have to actually share those private secrets? Did they actually have to share a and b? Nope. But were they still able to agree on the same key to use for their cipher? Yeah, they both get the same value of k. And so now thinking about the eavesdropping, which is again the big thing when thinking about cryptography, Eve can only ever intercept, okay, maybe she could intercept G and N, not a problem, but she can only intercept KA and or KB, because those are the values that are actually transmitted through the channel. Is it possible for Eve to get A or B directly from the transmissions? No, because Bob and Alice aren't ever actually transmitting A and B. They keep those private, okay? And so the idea then is if E wants to know, let's say A or B, because those are the values Eve is going to need to know if she wants to break this encryption and break this cipher, she would have to undo maybe Alice's operation where she said, well, Ka is equal to G to the A mod n. Even if Eve knows Ka, G, and n, that is a hard problem to solve. Hard meaning very expensive, requiring perhaps a lot of time. Okay? Is it possible to solve it? Absolutely. But it's very hard to do. And so based on the information that's actually transmitted, we're betting on the fact, when we design the system, that Eve is just not going to take the time needed to do this. Sort of, again, the idea is if you're sending me an email asking when are my office hours, is it going to do you any good if it takes me 3 years to determine that's the question you asked and then respond? Are you going to care what my office hours are this week 3 years from now? Probably not. Okay? And that's what this is all betting on. Does that make sense in some way? A little bit? We can work through an example? All right. So here on our next slide, and I apologize, there's going to be sort of a little bit of back and forth here because we've got the equations on the last slide. And so we can plug in some numbers and see how this all works. So suppose at the beginning, Bob and Alice do a little bit of communication, and they agree on the two values, n equals 23 and g equals 4. Okay. Now, is n a 300-digit long integer and is g a 100-digit long integer? No, but I don't think we need to go into that level of detail to show that this works. Okay? And so that's sort of our step one, if we go back up here. And so for steps 2 and 3, Alice chooses an value A, Bob chooses a value B, and so we can just say, well, Alice has her private key or her secret key. She's going to have as A equals 7, and Bob is going to use B equal 5. Any issues so far? Okay. So the first part here, we want to know what is Alice's public key Ka. Well, we can come back over here, and Ka is equal to G to the A mod n. And so we can start to work on what that would be. Okay, and so G is 4, A is 7, and N is 23. We could go through all of the modular exponentiation tricks that we did last time. 4 to the 7 is probably small enough that your calculator can handle it without much issue. Does anybody have 4 to the 7? 16,384. And what is 16,384 mod 23? If anyone's got that. We get 8. Okay. So I'm going to back up here and just write that there in the interest of space. Okay, so what this is saying now, this K sub A value, so this is that public part that Alice is going to share with Bob. When they do that communication, Alice is sharing 8. Notice, is 8 equal to her private secret? No, because A is equal to 7. So this is now some number derived using the private secret, but it's not actually that private secret itself. Okay? What do you think? Let's see if this works. Nope, we're going to run out of space. So the next question, what is Bob's public key? KB. Okay, does anybody remember how do we calculate Bob's key? Exact same way. So we're going to have now a KB, and now we're going to have G to the B mod n. Okay, so now we're going to have 4 to the 5 mod 23. And 4 to the 5th, I think it's 1024. So we'll get now 1024 mod 23. And that comes out to be, for those of you that are plugging along at home, about 12. Okay? And so again, we get Bob's going to share the number 12 with Alice. And is that equal to the actual private secret that Bob is trying to keep? No. 12 is not 5 by most definitions. Depends what your definition of is. Okay. So now that we've got those two, we can continue on and see. So if we go back a slide, we now get, okay, so Alice shares Ka, we've got that, Bob shares Kb, and now when we look at both of them, we need to see, do Bob and Alice get the same value of the key? Using these formulas, where now Bob is going to compute Ka to the B mod n, Alice is going to get Kb to the A mod n. And so what we want to do now is figure out, well, first of all, what is that key? And second, to verify, do Bob and Alice agree on it? Because obviously they should. If they don't agree on that key value, is this a particularly good cipher? Or good setup? No, it's probably going to be terrible. Okay? So the way Alice is going to do this is Alice is going to say her key K is equal to Kb that she gets from Bob to the A mod n. Well, what was Kb? What's that value that Bob was sharing? We got 12, right? Because that was what we had from that last part. So she's going to put in a 12. Now, what is her private part, that A value? It's just 7. So we're going to get 12 to the 7th mod 23. 12 to the 7 is, again, probably a small enough number your calculator can handle it, no problem. It's going to be, I don't know, 2, 3-ish million.
3, 5, 8, 8, 1, 8.
Yeah, so about 3.5 million. And if you take that in your calculator and you mod it 23, what do you end up getting?
Actually, that's 35 million.
It was what?
35 million.
Oh, 35 million. Okay. Sure. Yeah, it's a 7, not a 6. I can estimate in my head. Okay, so it's about 35 million and change. And when you take that modulo 23, what value do you get? I get 16. Okay, we agree. So what we now see is that Alice now thinks the key is 16. Now we have to verify, what does Bob think the key is going to be? What value would we expect? We would expect 16. Because if it's not 16, again, that says something went really, really wrong, and Bob and Alice are not going to agree on the key, which means they're not going to agree on a cipher, which means secure data transmission is going to be a nightmare. Okay? But the way this works for Bob, remember, Bob doesn't necessarily know the value A. Does Bob know KB? Looking up at the previous formula? Sure, he computed it. But he doesn't know A. So can he use that same expression for finding the key? No, we got to switch it around a little bit. And so Bob is going to have to use Ka, that public part that Alice shared with him, and raise it to be his secret, mod n. And so what was our Ka value? What did Alice find to be that value that she was willing to share? It was 8. Again, we got that sort of earlier in the example. What was Bob's value B? What was his private color? 5. Just right up there. And a mod 23. Well, 8 to the 5th is 32,000 and change. And when we mod that by 23, what do you think we're going to get? We're going to get 16. Okay, so do Bob and Alice now agree on their key? Yep. Does that mean they're going to be able to agree on a cipher? Yep. And does that mean we can now think about doing encrypted and secure communications? Absolutely. And again, the key idea here is the only parts that Eve was able to intercept, okay, maybe the G and N at the beginning, but were these KB and KA values. And from those, it is very hard for her to determine A and B. And without knowing A and B, it is very hard for her to determine the actual value K. Okay? KA, KB, G, and N make it very difficult to determine K, if that's all you know. Okay? And that's what makes this work. Any questions on this example before we move on? Okay. So sure enough, we get 16. So there's some limitations of Diffie-Hellman exchange. This is sort of where this idea of public key cryptography all started. And it's a wonderful example to work through, but it's not necessarily the entire story. And so what we've seen is that Diffie-Hellman exchange is useful for setting up keys and for getting everyone to agree on what's that key, that value K. Did we actually encrypt anything in that last example? No, we just said, here's the key we're going to use. We both agree on this value, even though we didn't have to meet in advance and tell each other we're both agreeing on 16. Okay? So maybe the question now is, how do we actually go about doing the encryption and the decryption? Now that we can get people to agree on a value without having to exchange the value, how do we use that for the encryption and decryption? And so what usually ends up happening is we're going to have to use something a little bit more complicated. It's not bad. And this cryptosystem is called the RSA algorithm, RSA being named after Rivest, Shamir, and Adelman. This was, again, going back to MIT in the late 1970s. This is still predominantly the algorithms that are used today to do cryptosystems. Notice they're now 40 years old. Do you think everyone on the planet knows how to break these things? Yeah, they do. It's actually really straightforward to write down how to break this. Why does this cryptosystem still work? Because it takes a huge amount of time. We know the steps. You can write down, you can put together an algorithm to break RSA encryption. I'm going to guess in probably between 10 and 15 lines of code. But you better wait 10 years for it to run. Okay? So again, everyone knows the algorithms that are being used. Everybody knows how this works. What makes it a good system is that it's very hard to crack. It takes a lot of time. Okay? And so again, what we're going to do is, just like with the Diffie-Hellman, we're going to have some sort of private and public parts. Now, not being used so much as the key, but actually as part of the cipher. How do we actually go about doing the encryption and the decryption? And we're going to be trading those back and forth. In some cases, we might want to still use Diffie-Hellman exchange to actually set up what are some of these values and to agree, although in other cases it's not going to be entirely necessary. Diffie-Hellman was sort of a warm-up to where we're actually headed. And certainly if you want more information, Wikipedia is a good source in this case. The Khan Academy also has a nice discussion or tutorial if you want to see a little bit more. Okay, so now we're finally at the point where we can define what do we mean when we want to talk about public key encryption. And I apologize for the huge quote here from Wikipedia, but it does a really nice job. And so the idea is now public key encryption systems are based on mathematical problems that currently admit no efficient solution. So this is that idea of it takes a long time to crack. There's not an efficient way to break it. It is computationally easy for a user to generate a public and private key pair and to use it for encryption and decryption. What does this mean? It says, well, Bob and Alice don't really have to spend any effort to set anything up. And they don't have to really use any effort to do the encryption or the decryption. The only place a huge amount of effort is required is if you don't know all of the private information and you're trying to crack the system. That's going to be hard. So the strength lies in the, quote, impossibility, they put here parenthetically, computational impracticality for a properly generated private key to be determined from its corresponding public key. And we'll talk about what private and public keys mean in a moment. Okay. And so thus, the public key may be published without compromising security, thus why we call it the public key. Do you expect things that are public to be secure? Not usually. Security depends only on keeping the private key private. Thus why we call it the private key. Okay. And so here's where sort of this differs a little bit from the Diffie-Hellman. Public key algorithms, unlike symmetric key algorithms, do not require a secure channel for the initial exchange of one or more secret keys between the parties. So in the Diffie-Hellman example, did Bob and Alice have to agree on something at the beginning to make it all work? Yeah, we had those G and those N values. In certain cases, that's not really that big of a deal. In other cases, that could be really limiting. And so the strength of going beyond that into something like RSA is we don't have to have that initial contact when we now want to think about how do we set up the cryptosystem and how do we do encryption and decryption. We don't have to have that agreement in the beginning. Okay, so the way that this is going to work, again, I apologize that the graphic is a little bit low resolution, is unlike the Diffie-Hellman case, we're now going to have what's called an asymmetric relationship. So think back to our Diffie-Hellman example. Did Bob and Alice both basically do the same things? So they both agreed on G and N. Alice computed KA after choosing an A value. Bob computed KB after choosing a B value. Were those two operations different? No, you just put in a different value for A or B. They shared their values, and then when they were done, they used the value that they received, did some stuff. Again, did they do different things? Nope, they did the exact same thing. That's what's called a symmetric system, and so that was what the terminology on the last slide was referring to. When we're now going to talk about RSA, it's going to be what we have called an asymmetric system, which is to say the sender and the receiver are going to follow two different sets of steps when the sender wants to encrypt the data, then when the receiver wants to receive and then decrypt the data. Okay, and so the way this is going to work is the sender is going to start off and have what's called the plain text. This is their message. Remember, there's a quiz in 17 minutes. I send out that email right now. That's the text, okay? Perhaps a little bit not useful. It's a little bit late for a reminder, but okay. And so I'm going to encrypt it because I don't want someone who's not in the class to learn that message and come quiz crash us. There's not enough seats, okay? I know it's popular, but we just don't want that. And so what I'm going to do is I'm going to ask you, you're the receiver, send me your public key. And you're going to send that information to me. What goes into the public key, we'll see that in a little bit. But you're going to send me the public key, and I'm going to use your public key to encrypt the data, to encrypt our message, and get ciphertext, which is now going to be just a bunch of gobbledygook. Okay? I then send you the ciphertext, you receive it, and now to decrypt it back into the plain text to remind you that we now have a quiz in 16 minutes, you're going to use your private key to do that. And that's going to allow the decryption to turn it back into plain text, which makes it readable to you. And so notice now, when we think about this idea of public and private key, where did my key, as the sender, where did my key enter into this? It didn't. I don't need to use my set of keys to send you an encrypted message. All of the encryption and decryption happens using the receiver's key values. Okay, and so we can already start to see that asymmetry in that. In the fact that the sender doesn't use any of his or her keys, we only use those from the receiver. Okay? Does that sort of make sense? All right. So basically, what's going to happen now is we're going to have to use two keys rather than the one in Diffie-Hellman to do this, where now we have sort of this public key that we're willing to exchange. Okay? And that's what we're saying, okay, well, you want to send me a message. I will send you my public key and use that to encrypt the message. And again, we'll talk about next slide or two, sort of what all of this information actually is. And then what I'm going to keep on my end is a private key that says, well, if you encrypted something using my public key, I have the private key myself that says how to decrypt it. Now, do I want to publish my private key? Do I want to share that with anyone? No, because if that gets out, then anyone can decrypt any message that was supposed to be sent to me. And that sort of defeats the whole purpose of this exercise. Okay? And so as we already said, what this basically boils down to is that the sender and receiver are no longer equal when we're going to do these systems and do this type of exchange. And so one other thing, and I'll mention this now, and we'll come back to it, it'll certainly be on Monday. The public key, we've already seen, or at least said, can be used to encrypt messages. It can also be used to verify signatures. So where might the sender's key actually become important? And why might we use these in a communication? Well, if I'm sending the message to you, I'm going to use your public key to encrypt, and we use your private key to decrypt. How do you know the message came from me? I can certainly put the text in the message, hey, this is from Matt. You have a quiz in 13 minutes. Okay, but do you necessarily know that that came from me? Could someone else just as easily have typed that into the keyboard and sent it to you? Yeah. So what can we do? I can use my key pair to sign the message and sort of use my private key to somehow embed my signature in the message. You then receive the message, use your private key to decrypt it, but then come to me and you say, well, you know where I am on the internet. Hey, Matt, send me your public key. I send you my public key, and you can verify that I actually signed it, which is to say that I'm the person that actually sent the message to you. Okay? So we can see that. We'll come back to that point a little bit later. But this is sort of the general idea. Every person that's going to be doing secure communication has a public key and a private key, and they can be used in various ways to make sure the communication happens securely and between two parties, and you know the identity of both of those parties. Before we get into the guts of this, does anyone have a question? Okay? So, actually, I guess one more slide before we get into the guts. So the key concepts behind public key encryption, that pun was absolutely intended. As we've said, it's computationally infeasible to find the decryption key knowing only the algorithm, which is to say, I put out my public key for the world to see so that you can send me messages. Using only my public key, can you determine my private key? I mean, the answer is yes, but it's going to take a really long time. Okay? This is why we use those really big integers when we're setting everything up, because it just makes the problem very computationally hard. But yet, if I have my private key, or you have your private key, and we've got the right key pair, it is computationally very easy to actually do the encryption and decryption, to do the signature and the verification. That's all very straightforward if you actually have the appropriate private key. And so this idea, number one, is really important, because if it's violated, this whole idea of public key encryption breaks down. Which is to say, if someone were to suddenly find a really, really quick, efficient way to factorize prime numbers, would this type of encryption be reliable anymore? No. Because then any eavesdropper who would have access to my public key would be almost instantly be able to determine what is my private key, and therefore they could decrypt any message that was sent. Okay? Now, the good news is, we don't know an efficient way to do that, at least not that will run on a classical computer. How many of you have heard of quantum computers? A couple people? Okay. So there's always this idea of how can we do computing better? We talked about this a few weeks ago when we started this whole digital devices unit, where we saw, the original computer was anybody remember from like 3 weeks ago, 4 weeks ago? What did we use as our original computers? We used our fingers. Okay, and we sort of went through time, and we had an abacus, and then we had sort of these big vacuum tube machines, and now we have these small transistors. We're always sort of exploring what are different ways to do computation. And there's a big field of research that's very, very popular right now, which is to say quantum computing, which says, can we develop computers basically using atoms and quantum mechanics rather than silicon-based transistors? And there's a lot of neat stuff because quantum computers can do a lot of things classical computers can't. Okay? Now, there's also a lot of things classical computers, something like the machine that you're using right now or that's displaying these slides. There are a lot of things those computers can do that quantum computers can't. So one's maybe not going to necessarily replace the other, but one of the issues is it's already known. It's about 20 years now. A physicist, I believe his first name was Peter, but named Peter Shor, came up with an algorithm that said if we had a fully functioning quantum computer, we can factorize prime numbers almost instantly. This is a problem quantum computers can solve very, very quickly. Should that be alarming? Yes, because what that means is, should a quantum computer ever become fully realized and available, what happens to all of our encryption? It's gone. It's absolutely useless. So 20 years have progressed. Do we now actually have fully realized, viable quantum computers? The answer to that question actually depends who you ask. Are they commercially available at commodity prices? No, they're not. But there are certain companies, D-Wave being one of the big ones, that claim to actually have very small but fully functioning quantum computers. Oh no. And so one of the issues that's now coming is when we're thinking about data encryption, as these computers get closer and closer and closer to full realization and deployment, we need to discover what's a different way to do encryption. And we have to completely fundamentally undo this, or redo this to come up with what's a way that we can now do the encryption and the decryption, but in a way that a quantum computer can't instantly crack. And it turns out this is actually a really big unsolved problem. So for those of you that are interested in, quantum physics or number theory or math, this is a really, really interesting area of ongoing research. It's not something I work on, but I know there are people on campus that do. And if you have any questions, you can take a look and find out. And just along those lines, I posted, there's a Nature article from a couple years ago that I posted to Blackboard for some background reading, if you're curious. You can also find out more on the blogs of the American Mathematical Society if you're interested in what some of those issues are going to be. But just take-home message from this part of the lecture, if you really value security, you could probably sleep tonight, but maybe not tomorrow night. This is getting close. Okay, so how does RSA actually work? This is going to be a slide you probably want to star. This will be very useful when working on some of the homework problems that will be posted later today. And so the idea is every user, as we said, who wants to use RSA to do encryption and decryption is going to have to generate a public and private pair of keys. Okay, so how does that work? Well, basically there are 4 steps. Number 1, that person is going to select 2 large prime numbers. Are 5 and 11 going to be large? Probably not. Okay, so again, these are going to be, each of these prime numbers are probably 100 digits long. Okay, so these are big numbers. But we can choose them, and we can choose any 2 that we want. It doesn't really matter. Okay. Second step, once we have those 2 prime numbers, we'll call them P and Q, we can compute the product. Just literally multiply P times Q, and we'll call that N. Step 3, we can choose, again, at random, some number, we'll call it E, E standing for encryption, such that E is in this range, it's bigger than 1, and it's less than the product P minus 1, Q minus 1. And, we need a second condition, E is relatively prime to P minus 1, Q minus 1, which is to say if we look for the greatest common divisor between E and P minus 1, Q minus 1, we get 1. Okay? Why do you think we're going to need these conditions? Why can't we just say choose some number E randomly? Why do we have to add these extra constraints? We're not going to go through this, but we need these extra things so that we can prove this algorithm works. If we violate one of those 2 conditions, our encryption and decryption routines are no longer guaranteed to work. Number theory can't prove everything's good. And so our encryption and decryption routines may not actually be inverses of each other. At which point, is this really a good system? No. Okay? So we've got to put these restrictions down just to make sure that everything's working properly. Okay? And so then, once we have E, and again, we can choose any E that satisfies these conditions, we can find a unique value D. D now standing, if E was for encryption, what do you think D is going to stand for? Decryption. And we can find it by saying the product ED modulo P minus 1 Q minus 1 is equal to 1. Okay? As it turns out, this is not a hard problem to solve, but it's more than I want to go into. So if ever I'm asking you about decryption keys, I will give you a series of decryption keys and ask you to verify to determine which one is actually the key. Being able to put in, if I give you a value of E and a value of D, can you verify that pretty straightforwardly? Yeah, just compute E times D, take the modulus P minus 1 Q minus 1, and check that it's 1. Like I said, it's not hard to solve, but I don't want to. It would take us another 30 minutes to deal with how to do that, and I don't want to take that time. Okay? But then once we have those values, so we've now got these 5 values. We've got P and Q from step 1, N from step 2, E, our encryption part from step 3, and D, the decryption part from step 4. We can set up public and private keys. And so our public key, sometimes called the encryption key, this is what I will share with anyone who asks me, is our value E, that encryption part, and the product of the prime numbers, N. Okay? What I'm going to keep privately to myself as my private key are the other 3 values. I'm going to keep D, that decryption key, private, and I'm going to keep P and Q private. Okay? What were those original prime numbers I started with? Okay? And so the idea now, right here you can immediately see, if we had a computer that was able to quickly factorize a number into its prime factors, what could someone do with that public encryption key? They could very quickly get from that value N that I'm willing to share, what were the values P and Q? Okay? And then suppose if someone knew the value E and N and also knew P and Q, is it hard for them to get D? No, not really. Because when I was setting up my private key, that's exactly what I had. I knew P, Q, N, and E, and was able to get D relatively straightforward. Okay? So that sort of is the crux there while we talked about the prime factorization. That's the rate limiting step. So when NSA is trying to break whatever security encryption or some hacker, all they're trying to do is figure out what are the 2 prime numbers that when multiplied together give N. That's it. It sounds really simple. Turns out to be really hard to solve in practice. Okay? And I think that's the place to call it today. We will certainly work through an example of this on Monday, but I believe it is now quiz time, so if you'll please clear your desks and leave out a writing utensil and perhaps a calculator, we will start distributing the quiz. Again, please wait until everyone has one and we say go to turn it over and start working.